Hello and welcome, class. Let us finish chapter 3. So if you're just coming off of part 3, which is obviously the predecessor to part 4, your brain might feel a little bit squishy, might be a little bit melty, and that is just the nature of trying to wrap your head around the quantum behavior of matter. We are going to round out, though, the story today, so brace yourselves. Bohr's model, which is what we discussed in part 3, is not the end of the story. We are now going to wrap that up. How is matter constructed? We are going to answer that question by introducing atomic orbitals, and just to give yourself a little bit of foresight, if you know of electron configurations, if you are looking forward to those or dreading them, we are not getting into that in this part. So we're going to be focusing on more of the matter side of things, the construction of the atom. And then in chapter 4 is where we are going to be introducing electron configurations and discussing their implications. So if you have no idea what I just said, just hang on tight and bear with me for the ride, and we will get there eventually. All right, let's finish chapter 3 though. All right, so again, Bohr's model, which we just talked about in part 3, first introduced in 1913, so just after turn of the century, built off of Planck's constant and Einstein's photoelectric effect, as well as Rutherford's nuclear model, tragically only works for the element of hydrogen. In Bohr's model, he states, again, as a little bit of a reminder, that electrons orbit the nucleus, and he stated that they did so in shells. Now, we haven't used the word shell yet, we've been using the word harmonic, but these are in reference to the n values. So n equals 1, n equals 2, where is it that the electron can be? In what harmonic is it? Now, what we refer to as the modern atomic model was introduced in 1926. Now, the word modern was thrown around a lot at the time, so like modern art, modern architecture, modern, etc. The modern atomic model is not necessarily in reference to it being the most up-to-date, but rather is a reflection of the times. So modern was the word being used to, at the time, introduce the new, the novel, the nouveau, the exciting. It's not to say that the modern atomic model is completely incorrect. Again, it's a really great foundation, but quantum mechanics has definitely evolved from what we are going to be talking about in terms of the modern atomic model. But this is the most advanced that we are going to get. If what we have been talking about so far excites you, I hope you continue into studying physical chemistry, quantum chemistry. That is really where we flesh out all of the details and work out the technicalities. If what we have been talking about so far, though, has kind of been turning you off from chemistry, again, I implore you just to hang on a little bit tighter. This is as detailed as we are going to get when it comes to our description of quantum chemistry. We are going to be introducing Erwin Schrödinger et al.'s method that works pretty well to describe the construction of all elements, as well as it does a pretty good job at describing how all elements interact with energy. The major difference between Bohr's model and Schrödinger's modern atomic model is that now we are kind of shifting the perspective a little bit and saying that electrons don't just exist in shells, so those values of n, but also exist in what we call subshells. These subshells are spread out in 3D space. They allow for more modes of motion. They give the electrons more places to roam. And in doing so, we allow for a greater breadth for atomic construction, and as a result, get better calculations, better predictive results about how the matter is going to interact with energy. All right, but what are these shells? What are these subshells? How is it that matter is actually constructed? That's going to be the focus of today's lecture. Well, the modern atomic model doesn't simply state that the electrons behave, again, or exist in particular shells, but in subshells that can be mathematically described using what we call wave functions. These are mathematic functions represented by the variable psi that are going to depend on position, so where you are in x, y, z Cartesian space, as well as time. How much time has the electron been allowed to move? In doing so, we can describe the wave-like behavior of the electron. We can really get a picture for what that harmonic looks like, mathematically speaking. We can actually visualize these types of wave functions, which is what we have down below. The 1s versus 2s, the 2p versus 3p, as well as the 3d. We'll do this a little bit. These are all different labels that describe not only where the electron is, but how it can move. So the S description, so the 1s, let's say 2s, we can see describe radially symmetric motion. The wave that is being depicted here in the 1s is very simply moving either up or down. It's like a simple trampoline motion, up and down. This represents the first harmonic, and not only the first harmonic, but the most stable form of the first harmonic. This is as chill as an electron can get. And you may be asking yourself, well, where's the electron? This is a flat surface. And I'm here to tell you that this GIF is meant to represent the electron and how its wave-like nature fluctuates around the atom. And that's, again, we're getting esoteric. This is, again, as esoteric as we will be getting. The flat surfaces here, as they move, describe the electron, whether or not it moves symmetrically up and down as a trampoline surface, or even with more like range of motion. Again, in our 2s, we are also radially symmetric. It's just instead of everything moving up and down at once, the center, it seems as though, is moving up and down in opposition to how the outer ring is moving up and down. So we have greater modes of fluctuation. In the 2p and the 3p, really what we can see here, what is being depicted is that the electron is sloshing back and forth like this. So the wave is moving up and down, kind of back and forth, back and forth. It's almost like if you take a pot of water and push it in one direction and then stop very suddenly, the water is going to slosh back and forth on the surface. And that's exactly what the electron in this mode of motion is doing as well. It's moving back and forth. The 3p motion is doing the same thing, but in much the same way as the 2s, we just now have more fluctuations, but in that same direction. Now the 3d, we are increasing complexity, right? As we move from left to right, really that's what we're doing. It appears as though now we have two modes that are in this direction, moving up and down in unison, but in opposition to the two modes that are in the cross of it, moving up and down. So instead of moving up and down in unison, we now have different pockets of space moving up and down. And that's really what each of these pictures are. How is the wave fluctuating? Now again, if this stuff really interests you in P-Chem or Quantum Chem, all depending on what your college labels the class as, what semester it's taught in, you will work through how these wave functions are constructed and map stuff like this for yourself. We in general chemistry are just observing the product of the mathematic functions as these surfaces in motion. We are now going to turn our attention away from the surfaces and towards what we call orbitals. This is what we normally think of when we try and picture where electrons are and how they behave. Mathematically speaking, the orbital is just the square of this mathematic function. So we're taking our wave function and we are squaring it. The result of doing so is that we actually find a pocket of space around the nucleus where there is a high probability of finding an electron. These are almost like balloons around the nucleus where an electron can be found inside of the balloon, but it cannot be found outside of the balloon, or at least not very easily. All right, so where we are moving from here, we're going to observe these different balloon-like structures. We are going to observe the orbitals. We're going to break down how an electron can exist in each of these spaces, and then we're going to call it a day. The labels that we use to describe these different orbitals are known as quantum numbers. The basic definition, again, a reiteration of what I just said, slightly different words, can be found here. quantum numbers describe the distribution of electron density, aka atomic orbitals, aka where is your electron in the atom. We need more numbers than just n. According to Bohr's model, n was all we needed. However, as our mathematic description of the electron has changed, we've actually found that we need more quantum numbers than that. We need something that we now call L. We need something that is called m sub L. Now, a good example of a wave function and its general construction we can see here. Again, we in this class are not going to go in any further depth than just seeing the wave function and moving on. But I do want to demonstrate at least a version, as we can see here, of a wave function because it helps to give these quantum numbers a little bit of context. At least in my experience when I was going through high school, it seemed like these quantum numbers just kind of came out of nowhere. They were arbitrarily used and like slapped on as labels for these different atomic pictures. I really want to show that yes, even though we're not going into any further detail than this, these variables have a purpose. They belong somewhere, and they are used to describe the electron in combination in some type of greater mathematic function. All right, so where we are going, again, just laying out the breadcrumb trail, not just behind us, but also we're looking at it in front of us. We are now going to describe all of the remaining quantum numbers. We're going to revisit n, which again is predominantly Niels Bohr's n equal 1, n equal 2, n equal 3, etc. We're going to reframe it in terms of the modern atomic model, and then we are going to introduce the rest of these quantum numbers. The L, which we can see present in this equation, the m sub L, which we can see in this equation, and the m sub S, which is strangely not present in this equation, but also has pretty significant meaning. It was just found a little bit later, so we're going to talk about m sub S as well. There are 4 total quantum numbers which we use to describe the location of an electron. All right, so as we are moving forward, here's an analogy that we can think about and I'm going to be returning to. Since we are using these quantum numbers as a means to describe where the electron is, let's just think of all 4 of them in combination as some type of address. Right, if we're using them to locate the electron, we can think of the n as being a very wide spread depiction of like what the general energy level of our electron is. This is going to represent the city. Our L is going to get more specific. It's going to help narrow down the location a little bit. This we can think of as the street address. The M sub L is going to narrow it down even further in 3D space. This M sub L gives us the home address. So we need each of these 3 pictures, the home number as well as the street as well as the city, to figure out exactly where we are going, where is the electron located, in what suburb can it be found. The M sub S is even more specific than that. This is going to be a label for the occupant themselves. Are you giving it to Mr. Smith or are you giving it to Mrs. Smith? This is what M sub S is going to represent. All right, so let's start with the city. We're starting with the big picture. Then we're going to talk about the street addresses, how we narrow down the location of the electron, the home address, which we use to narrow it down even more, and then finally, which occupant are we even talking about inside of this orbital? All right, so n represents what we now call the principal quantum number. This n represents the shell of the atomic orbital, or as we labeled it in part 3 of this lecture, what is the harmonic that we are referring to? Are we in the first harmonic? Are we in the second harmonic? Are we in the third harmonic, etc.? This shell we have also found to be proportional to the size of the atom as well as the energy of the orbital, where n is equal to 1 has the least energy. It is the most chill. That's a C, most chill. N equal to 3 and higher are going to be high energy, right? The higher the n, the higher the energy. Now, the values that we can use numerically to represent this n are integers only, starting at 1, right? We have to have at least the first harmonic. First harmonic. But if the electron is even a little bit more excited, we're going to be in the second harmonic, n equal to 2. Even greater than that is the third harmonic, n equal to 3, ... whatever n. As long as it's an integer, it can represent where the electron generically is in terms of energy. Quantum number L, which in the font that I am using on my slides looks like a 1. Whenever I write it, like with my hand, I always write a little cursive L to make it really clear that it's not a number 1. Angular momentum, quantum number L, where I just said it, L is known as the angular momentum quantum number. This represents the subshell of the atomic orbital. So we're narrowing it down. It's not just about how much energy the electron is, it's also about where it is in 3D space. In what direction is the electron moving? Is it moving back and forth? Is it moving in two directions, kind of perpendicular to each other? Is it all moving unanimously up and down together? How is the electron moving in 3D space? The way that we represent this is by using, again, quantum number L, which is going to depend on the value that came before it. It's going to depend on n. And the reason why is if your n is low, if your energy is low, the electron cannot be moving in a more exasperated or exaggerated way. That is going to imply that you need high energy. So if your value for n is low, you're more than likely going to be moving in a really relaxed kind of back and forth way. If your n is high, you have the ability to move in these more complicated ways. Now, the way that we represent this mathematically, again, with our value L, is that it cannot be any greater than n. It can't even be equal to n. It has to at most, be equal to n minus 1. It, however, can go as low as 0. So it has to be, L has to be represented by integers, similarly starting at 0, but it can go only as high as n minus 1. So let's return to our address analogy. Let's say we're looking at a particular city. Let's say, since I'm originally from Minnesota, I'll just go with like Minneapolis. So let's say we are looking at the city of Minneapolis. This is going to represent, or in this analogy, this is going to represent our n. Well, let's say that there is a street that the electron is living on, right? Where again, the street is represented by this L. Well, you can't choose an L, a street, that is outside of the city that you are working with. Let's say we consider the street Dalmar Drive, which, if there is a Dalmar Drive in the city of Minneapolis, I had no idea. Dalmar Drive is actually in the city of Brainerd, Minnesota, which is, fun fact, my hometown. So Dalmar Drive cannot be used to try and further describe where the electron is in the city of Minneapolis. It just doesn't work. So we need to make sure that our L, which is supposed to represent, again, the street, works with the city, the N, that has already been defined. So if N is equal to 3, we could have 3 different possibilities for what the L could be equal to. We could have L is equal to 0, we could have L is equal to 1, we could have L is equal to 2, and that's it. All depending on what city your electron is in, this is going to narrow down the street options for where the electron could even further be located. All right, so what we have so far is well and good. Each of these L's representing kind of conceptually the streets where we are can be narrowed down, again, all depending on what N we have. However, the L not only tells us the direction the electron is moving in 3D space, but also gives us the shape of the orbital itself in 3D space. So what we're going to do is spend a fair amount of time now looking at what are all the different streets that your electron could live on? What are all of the shapes of these atomic orbitals? And we are going to start with the small. L is equal to 0. This is the lowest energy option. And we call this the s orbital. Now the L equal to 0 label always corresponds to an s orbital. Similarly, if your electron is in an s orbital, if you're told that information, your L is going to equal 0. I forget what the term is in logic and rhetoric, but this is a statement that is true in both directions. L equal to 0 does mean an s orbital, and an s orbital does mean that your L is equal to 0. That's going to be true for all of the orbitals that we are working with here. So s orbitals, in terms of picture, are like onions, right? They are layered, much like ogres. I'm sorry, I can't even say that without laughing. Oh man, I am such a product of my times. Okay, so s orbitals are like onions. There are a number of nodes that we can find inside, and these nodes basically represent where we have no onion. They are between the layers. And we'll describe what both of these break down to in a second. But in terms of picture, we can see on the right, the 1s orbital is the simplest. It has no nodes. Again, this represents the first harmonic in the most simplest and straightforward ways in 3-dimensional space. We have a nice closed surface. There is nothing discontinuous or wrinkly or broken or punctured about it. There are no gaps. And similarly, if it were to fluctuate, it could fluctuate radially in all directions evenly. So we can think of this, again, in terms of the string example from part 3, where we have that nice even fluctuation of our string up and down. Now, as soon as we increase in complexity to the 2s, where the 2 now represents the n that we are working with, and the s represents the L that we are working with. So this is always the notation that we see. The number that's listed first is the n. The letter that's listed second represents the L. So 2s means that we are working with n equal to 2, L equal to 0. And this is a valid combination, again, based off of the previous boundary conditions that we can find or defined. All right, so in a 2s, we can see that there is one node here. There is one gap between the layers, where the inner layer is this orange and the outer layer is this teal color. If we increase in energy to the 3s, so now n is equal to 3, L is equal to 0, we can see that there are 2 nodes. So there are 3 different layers, 2 nodes in between, where these nodes represent the gap between the layers. Now, as we continue increasing in energetic complexity to 4s, 5s, 6s, etc., we're also going to increase the number of nodes each time. Now, we can calculate how many radial nodes we would predict by taking the n. So let's say, for example, if we're, again, returning our attention to the 2s, n is equal to 2, and we're going to subtract out 0, since this is an s orbital, plus 1. So 2 minus 1 gives us 1 radial node, which is exactly what we see in this picture right here. There's one gap between the 2 different layers. Now, we also have labeled here that there are 0 angular nodes. There are no gaps as a function of angle. This can be more easily explained, like what an angular node is, when we turn our attention to L equal to 1. So let's put a pin in this. But when it comes to s orbitals, there are no angular nodes. We'll further define what an angular node is when we can actually see a picture of one. All right, so the last thing to address before moving on is that the smallest possible s orbital that we can have is the 1s, and that is what is pictured right here. The way that we can reason through this is that S, again, implies that we are working with an L that is equal to 0. And if L is equal to 0, the smallest our N can get is going to be that very small L plus 1, which is equal to 1. And this comes from, just to go backwards one slide, this comes from the previous definition. I'm going to clean this up a little bit, right here. The maximum value of our L is going to depend on N, and similarly, the minimum value of N is going to depend on L. So if our L, for instance, in the orbital we're working with is equal to 0, the very smallest that our N can get is 1. And the reason why has to do with this boundary right here. N can never be equal to L. Your street always has to be found within your city. It cannot be equal to your city. All right, so this was our description of the s orbital. Again, L is equal to 0. We can see the shape is a perfect sphere. They are layered as we increase in energy, like onions. And we can predict exactly how many radial nodes there are, all depending on what the N and the L combination is. The smallest value for an s orbital we can get, the least energetic, the most chill, is 1s. All right, the next highest in energy, L, that we can have is 1, right? We're just increasing in integer value. If our L is equal to 1, what this signifies is that we are working with what is known as a p orbital. So we are now fluctuating in higher dimensions of space. We are in a higher energetic space. If we're working with something that is labeled as a p orbital, similarly, by necessity, by definition, this is also going to correspond to an L that is equal to 1. So if you're told, hey, you're working with a p orbital, you know your L is equal to 1. Now, p orbitals have the shape of dumbbells. You can kind of see that illustrated here on the right. The way that we can calculate how many radial nodes we have is the exact same equation as we've previously seen. If you know what your N and your L are, you can calculate how many radial nodes you have. And the reason why this equation is consistent is the s orbitals, we described them as appearing like onions, right? They have layers, but as it turns out, every orbital can have layers. As we increase the amount of energy we are working with, we are going to increase the number of radial nodes or layers we have. So each of the radial nodes gets introduced via a new layer on your orbital. The way that we calculate how many radial nodes we're working with doesn't change as a result. All right, here though, we have a new type of node that we can talk about, where a node, I just realized I never actually formally defined, I said it was the gap in between the layers, but really what a node signifies is a location where an electron cannot be. Mathematically, it is equal to null space. It cannot house an electron. An electron is not there. So angular nodes are pretty interesting. They are also known as nodal planes. We can picture them almost like sheets of paper that you can introduce or slice, place in between pockets of space where an electron can be. They cut your orbitals in half. So a p orbital, as we can see illustrated here on the right in its most simple depiction, has one nodal plane. There's no equation to calculate. Each p orbital has one angular node inside of it. And the angular node in this particular orbital we can see is cutting the orange piece and the teal piece in half. Directly in between the orange and the teal, there is null space. An electron cannot be there. If we were to look side on to the picture of this p orbital, what we would see is something like this. There is a perfect little gap. The reason why this gap is known as a angular node, first of all, again, just returning to the notion of the nodal plane, we can think of an angular node as being represented by a piece of paper. If you can slip a piece of paper in without cutting your surface, this means that it is representing some type of angular node. Now, by definition, what the angular node means is, let's say this is the nucleus, this is some type of like vector in space, and we want to keep the distance, the length of this vector the same, so we're going to keep this same distance right here, whatever this distance d is, but we are going to move it as a function of angle. Now, as we rotate this arrow, rotate, 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 what we can see as we move the arrow from being like flat upwards is it now is entering this pocket of space as a function of angle where there is no orbital. There is one emptiness, one pocket of space where there is no orbital as the vector moves from right all the way down to left. Anytime your arrow enters null space where there is no orbital, this means that you have an angular node, and the test moves in 180 degrees. So from here, we are in an orbital, we enter one space where there is no orbital, and then we go back into space where there is orbital again. One location as a function of angle where there is no orbital means that you have one angular node. Now again, the paper trick is going to be the easiest way that we can use to illustrate whether or not your orbital has an angular node. So there are actually 3 different p orbitals. Each one of these p orbitals is energetically the exact same. The only difference is the direction that it is facing in 3D space. So we can see that the first p orbital here is lying on the x-axis. This is our x orbital. The central one is on the z-axis. This represents the z orbital. And the third is along the y-axis, which represents the y orbital. Each of these unique, orthogonal in 3D space. The smallest that we can possibly have, the lowest of the low energy for p orbitals, is a 2p orbital. There is no such thing as a 1p. The reason why comes down to, again, how we're defining each of these terms relative to each other, each of these variables. L is our p orbital, out of necessity, is always going to be an L that is equal to 1. L is equal to 1. And according to our boundary condition, the smallest that n can be is this L plus 1. Our n has to be equal at the smallest to 1 plus 1, or 2. So that's exactly where this 2p label comes from. Our n is the 2, our L equal to 1 is the p. All right, next up, we're just increasing in complexity here. L equal to 2 gives us what we call d orbitals. Now, d orbitals, for the most part, look like clover leaves. There are like 4 little pockets of space where an electron can exist, at least as we can see illustrated in the furthest left 2 and the furthest right 2 d orbitals down below. There are 5 unique d orbitals. Mathematically, each of these, again, is orthogonal in 3D space, meaning, mathematically speaking, that each of these 4 are truly unique, even though they might look similar to us in 3D space. The number of radial nodes, again, is going to be equal to this equation here. Our n is going to be equal to whatever the energy level we're working with. L is going to be equal to, in this case, 2. And we are going to, as we increase in energy, introduce more radial nodes, again, as a function of layering. The number of angular nodes that we have for the d orbitals, though, this is where we are truly unique. Compared to the s orbitals and the p orbitals, we now have 2 angular nodes. In other words, there are 2 pieces of paper that you can slip in between these orbitals without ripping the piece of paper or without puncturing the orbital, and you would find a perfect location of nodal space, of null space. It's kind of easy to see in the cloverleaf shaped orbitals, like the 2 on the left and the 2 on the right, where these pieces of paper can slip. So like in the, like, let's look at just the leftmost one. We could fit a piece of paper right here in between these guys, and we could fit it perfectly horizontal in between the lobes right here. So there could be a piece of paper right here and a piece of paper. I kind of messed that up in 3D space, but the piece of paper, there, would look like this. It would cut it in half this way. And the same could be said for each of the other clover leaves. You can fit 2 pieces of paper in between. All right, but what about this central orbital? Definitely doesn't look like a clover leaf. How chemists refer to this orbital is the donut orbital, because there's this little donut right here along the plane. Well, how we can represent or figure out where the nodal planes are here is actually, there's no rule mathematically that states that you can't roll or fold without creasing, but just curve the piece of paper that we're working with. So it turns out that the 2 nodal planes in the donut d orbital, we can roll into cones and place them right here. So there's a cone that can fit right up in here, and a cone that can fit down below. These are going to represent the 2 nodal planes in the donut d orbital. All right, so again, there are 5 d orbitals total. Each of them are unique, and the smallest energy level that we can have is the 3d. And again, this comes out of the necessity of how we have defined our variables. If d is always going to represent L equal to 2, this means that the smallest that the n can be is 2 plus 1, which is equal to 3. So the, again, more complex your street address is, the larger your city is going to have to be to accommodate that more complex street that runs through it. All right, the last orbital that we are going to introduce is known as the f orbital. This is the most complex of the orbitals that we are going to look at. There are higher energy orbitals than this. Again, if we are working with integers, there's no reason that L couldn't be equal to 4, 5, 6, 7, assuming that your n is also large enough. But the lowest, or this is the highest like ground state, or the highest naturally occurring orbital that can exist in a stable low energy atom. So L equal to 3 corresponds to an f orbital, and again, the f orbital corresponds to L equal to 3. The 2 are reversibly true. The f orbitals are shaped like double clover leaves. I mean, that's kind of true in some of the orbitals down below, the furthest to the left and the furthest to the right. Some of them are more like hexagonally shaped. So like these 2 here are kind of, they're like 6 lobes that are kind of in like a hexagonal sort of orientation. And then we have this guy in the middle, which is what chemists refer to as the double donut, because there are 2 little donut shapes in the middle. And I'm sure like chemists everywhere don't refer to the central like d orbital and this central f orbital as like the donut and the double donut, but most chemists that I know here in America do. Maybe that's telling of our culture, I don't know. But I also find it amusing, and like when you're studying something as like technically serious as chemistry, why not have fun with it? All right, so the number of radial nodes that we have follows the exact same equation as before. Again, if you are taking an orbital and you are layering additional pieces on top of it, like so, you're always going to introduce these in-betweens, these radial nodes in between your layers. And we can find how many radial nodes there are by using this very simple equation. Now, the f orbitals are mathematically unique to all of those previously because they have 3 angular nodes, or 3 nodal planes. Again, we can take our pieces of paper, either slip them in between these like little pockets of space, or roll them into cones and, you know, again, slip them in between the orbitals in these like pockets of space. But you may have noticed a pattern at this point. The number of radial nodes always follows this equation. Yes, it's true, but the number of angular nodes that a particular orbital has is so far and will always be equal to what your L is equal to. Our s orbital has an L that is equal to 0 and has 0 angular nodes. Our p orbitals have L equal to 1 and they have 1 angular node. d orbitals are L equal to 2, and they have 2 angular nodes. And here, as we are seeing, the trend is starting to really become apparent. F orbitals with an L equal to 3 always have 3 angular nodes. And this is always going to be true. If you know your L, you already know how many angular nodes are you working with. The two numbers are going to be exactly the same. The smallest of all of our F orbitals that are possible are going to be the 4F. So there's no such thing as a 3F, there's no such thing as a 2F, there's no such thing as a 1F, because out of necessity, if L is equal to 3, then the smallest n that you can viably have has to be equal to 3 plus 1, which is 4. Your street must exist within your city. Your L always has to be less than your n. And if we're working with integers, the smallest n that you can have, if your L has to be 3, is 4. All right, so what we've done so far is lay out the city, the n, and we've laid out the different types of streets that your electron can live in, which are your L's. Let's narrow it down even further. Let's narrow down that home address. The magnetic quantum number is known as the M sub L. I'm saying sub because the L is found in the subscript. So M sub L. It's not a 1. I know, again, my font is not the best here. Arial fonts or sans serif fonts don't really help to characterize L's versus 1s, but this is an L. So M sub L is going to represent the orientation of your orbital in 3D space. So for example, we've previously said when it comes to p orbitals that there are 3 unique p orbitals. How we label these, or at least before, we labeled them using x, z, and y. These are the 3 different directions they can face in Cartesian space. The magnetic quantum number gives us a numeric representation of this as well. The values for your M sub L are going to depend on L. So when it comes to the p orbitals, L is equal to 1. M sub L always runs from negative L to positive L. And we are going to include 0 in between. So in the example below, our x, let's say, when it comes to the M sub L assignments, we'll give this one the negative 1. Since L is equal to 1, it has to, or the M sub L's have to run from negative 1 through 0 to positive 1. And that's it. This is as narrow as the home address can get, right? Again, your home address has to depend on what street you're living on. You can't label a house that is on some other street. So the M sub L assignment is always going to depend on the L assignment. If L is equal to 1 in this case, we can see that there are 3 unique options for an M sub L. This is going to give us negative 1, 0, and positive 1. In fact, the M sub L assignment tells us how many unique orbitals we could draw in 3D pictures. So let's say if we go back to our F orbital, and I'm going to clean this slide up a bit. Since an F orbital always corresponds to an L equal to 3, we would predict, even without looking at all of these pictures down below, the M sub L values have to run from negative 3 all the way up to positive 3 and include every integer in between. So there's going to be a negative 2, a negative 1, a 0, a positive 1, and a positive 2. These are each of the unique orbitals that could be made or could be found within, these are all of the unique orientations that your F orbital could take. These are all of the unique pictures that you could make. We can see that there are 1, 2, 3, 4, 5, 6, 7 unique pictures. Just like how below, we can see that there are 1, 2, 3, 4, 5, 6, 7 unique pictures that we can draw. Now, each of these pictures, again, are derived from the mathematic wave function. We are not showing that math explicitly, but the label of the M sub L in the equation is what gives us these 7, in this case, unique pictures. All right, so that is the magnetic quantum number. The m sub L always has to run from negative L to positive L via each integer in between. The number of unique integers we have tells us how many individual pictures of the orbitals we can draw. All right, well, with all of the rules that we've talked about so far for N, L, and M sub L, and how each of the labels that we can write depend on the quantum number that comes before it, I'm going to ask you guys, which of the following sets of quantum numbers that follow the N, L, M sub L notation can't exist? Which of these collections of our quantum numbers breaks the rules that we have previously defined? I'm going to give you guys the chance again to think about what each of these combinations means. Do these numbers break the rules that we have previously talked about? All right, welcome back. Let's just look at each one in turn, piece by piece. So the first combination of quantum numbers, our n is equal to 2 and our L is equal to 1. Let's just look at each of these pairings in turn. Since each of the quantum numbers, again, depends on the number that comes before it, we're just going to observe each of the pairs and determine if the rules are being broken. Well, according to the rule for how we define L, L has to be less than our n, and it looks like this is fine, right? N2 is greater than L is equal to 1, so we're fine here. Now the M sub L, our boundary condition, our definition, states that it has to run from negative L to positive L. Well, it looks like if L is equal to 1, the positive L is positive 1. Everything here seems to check out. In fact, if we want to write the combination for what this would, like what type of orbital we're working with, n equal to 2 means we are working with a 2, and the L equal to 1 means that we are working with a p. Specifically, we're working with a 2p orbital that has some direction in space, some orientation. Now, all depending on which coordinate system you're working with, and specifically which coordinate is up, if z is up versus x is up versus y is up, this m sub L being equal to a +1 is going to tell us exactly which direction we are pointing. So it could be the x direction, could be the y, could be the z, but either way, we are in the +1 direction. And it's valid. This orbital can exist. No rules were broken. 2p orbital in some direction of space, totally fine. All right, next. N must be greater than L, and wouldn't you know it, this first pairing that we're looking at, it looks like our N is equal to L. This cannot exist. This breaks the rules. This is what we call a virtual orbital. We can write it mathematically, but physically it does not exist. All right, the last combination we're looking at here, the first pairing, it looks like N is greater than L, right, because 1 is greater than 0. Check, so far so good. The M sub L, again, has to be within the range of positive L to negative L. And 0, well, I mean, there's only one value you can really have. It's just plus or minus 0. You can't have a positive 1. That's outside of your range. You can't have a negative 1. That's outside of the range. And similarly, you can't have a negative 2. This is outside of the range, meaning that this orbital also is one that we could write mathematically, but physically does not exist. Our home address in the last example is off of the street that we are observing. And in the second example, we are trying to observe a street that doesn't exist in the city that we're observing. So both of these last two sets of quantum numbers do not exist. They do not represent an electron, or at least a position that an electron can be in real 3D space. All right, so it's been a lot so far. I recognize this. We've worked through a lot of different labels. We've looked at N, we've looked at L, we've looked at M sub L. So we've looked at the city, we've looked at the street, we've looked at the home address. All that is left is to observe the occupant. The occupant is represented by what we call the spin magnetic quantum number, or m sub s. So again, the s here is in the subscript. Now the magnetic spin quantum number, or m sub s, represents the orientation of the electron itself. Is the electron spinning clockwise, or is it spinning counterclockwise? Is it magnetic north end up, or is it magnetic south end up? The magnetic spin quantum number does not pertain to the orbital, but rather to the electron itself. And we numerically represent this question, right? Is it north end up or south end up, etc., by labeling the electron with a +1/2 or a -1/2. So this is the only fractional quantum number that we have. The reason why it is a 1/2, again, comes down to how the math itself, the more advanced quantum mechanics, kind of works out. And if you continue in studying, or in your studies with chemistry, you'll see where this 1/2 comes from. But here at the general chemistry level, all I'm asking is that you recognize that your m sub s can be +1/2 or -1/2. There are a couple of different other ways that we can say this. Either the electron is spin up or spin down. It could have an alpha spin or a beta spin. If it is spin up and or alpha spin, we call this the +1/2 version. This would also correspond to your electron spinning in such a way that because when anything that has a charge spins, it creates a magnetic field. If your electron is north end up, this is going to be your +1/2. If your electron is spin down or beta spin, the north end is down and it will have a -1/2 m sub s. So this is the equivalent then of, if you're writing a letter to an electron, you know its city, you know its street, you know its home address. Now all you need to do is give it a label. Are you referring, are you writing your letter or referring to your +1/2 electron or your -1/2 electron? One last example for the day, because we've seen how the quantum numbers can be written if we have the n, the l, and the m sub l present. Similarly here, we are going to see now how the m sub s gets incorporated as well. So we're going to list all of the quantum numbers following this notation that could represent an electron in either of these two following orbitals. So again, to reiterate, the 2 in front represents our shell, the n, and the p here represents the subshell, the l. So we're going to work through the first one together, and then I'll give you guys the chance to write out all of the quantum number combinations for the 5D case. So let's look at the 2p first. Well, if we're working with a 2p orbital, and we want to refer to an electron on the inside, there are so many different valid combinations that we could have. So first, we could be referring to an electron that is in the n equal to 2. Right here is the city. Our p means that the l is equal to 1. Here's the street. But let's say we don't quite know what the home address is. We've narrowed it down, but we don't know anything more detailed than that. Well, your electron could be in the +1 house. It could be in the 0 house, or it could be in the -1 house. These are the 3 different houses, the 3 different orbitals that your electron could be in. Similarly, if you don't know exactly which electron you're referring to and we want to know what all of the valid combinations are, your electron could be the +1/2 electron. It could be spin up in each of these cases, or it could be spin down. Now, if it's spin down, we could write out 3 separate sets of orbitals. I'll just do this here to be explicitly clear. So again, we're writing out each of the houses: 2, 1, +1, 2, 1, 0, 2, 1, -1. And if the electron you're trying to refer to is not up spin, if it's down spin, we have to write -1/2 for each of these. So many options. All right, so if our electron is in a 2p orbital, Assuming, again, we don't know anything more specific than that. We don't know if it's an upspun electron. We don't know if it's downspun, right? We don't know if it's Mr. Electron or Mrs. Electron. Let's say we're just writing it to the electron household. We have to include both the +1/2 and the -1/2 option. Either one could be valid. Similarly, if we don't know what the direction of our orbital is, we're going to have to include each of the home address options because we can't narrow it down any further than that. It may seem kind of like a silly analogy at this point, because if you're writing someone a letter, hopefully you would know their home address. But let's say you just kind of live nearby and you've never bothered to memorize their home address. Well, you're going to have to walk down the neighborhood and figure out where your friends live. So that's going to be our analogy here. So there are 1, 2, 3, 4, 5, 6 valid N, L, M sub L, M sub S combinations for an electron that could be found in a 2p orbital. Beyond this, like any additional combination we would write or could write breaks a rule in some way. So there are 6 valid and, technically speaking, an infinite number of invalid organizations for how an electron could be referred to in the 2p orbital. So these are the 6 valid ones. All right, so now that you've seen my approach and how to fill out the diagram here, what are all of the possibilities, all of the home addresses, and either or +1/2, -1/2 electron, I would like you to try and write out what are all of the valid quantum number combinations that could represent an electron in the 5d orbital instead. Welcome back. I am going to clear my slide. Boop. And upon clearing the slide, I have now made more space so I can also write out what all of the valid combinations are. All right, so the information that we are told, we know the N and we know the L. This means that we can write out the city and the street combinations again. So the N is going to be 5, the L is going to be 2, and this is it. So technically speaking, if N is 5, there's a whole bunch of different L's that we could in theory have, but we are told specifically that we are working with a d orbital, which means our L has to be equal to 2. And similarly, our N has to be equal to 5. So we've narrowed it down this much, right? Again, if you're trying to track down your electron in some particular neighborhood, at least you know the city and you know the street at this point. So we know our N is equal to 5, we know the L is equal to 2. Well, from this information, we can come up with what the M sub L range is going to be. Since L is equal to 2, the M sub L has to go from -L, which is -2, by integer steps all the way up to +2. So in between this, there's got to be a -1, there's got to be a 0, and there's got to be a +1. There are 5 unique and valid M sub L values. There are 5 valid home addresses for the electron if this is the combination of the neighborhood they live in. So we could have a 5, 2, -2. We could have a 5, 2, -1. A 5, 2, 0, 5, 2, +1, and 5, 2, +2. So there are 5 houses in the neighborhood where the electron that you are focused on could live. Now again, if your electron, if you don't know the identity of your electron any more than could be an electron, if you don't know the specific spin, it could be a +1/2 or it could be a -1/2. And so in the 2p case, I wrote out all of the 6 combinations specifically, like explicitly. What I'm gonna do here, just to save on some space, and this is a totally valid move that you could pull as well, is I'm gonna write +or-1/2. So now I'm not writing 2 different letters and giving each one to like Mr. Electron and Mrs. Electron. Now I am writing 1 letter and labeling it to Mr. and Mrs. Electron. In this given household, hopefully I found the right house. And I'm gonna do that for each of these combinations, +or-1/2, 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 and last but not least, +or-1/2. So we can see that there are 1, 2, 3, 4, 5 valid orbitals that a plus or minus 1/2 electron could occupy, provided that it is in a 5d orbital label. All right, so if we had any more information, like if we knew specifically what the home address was, aka if we knew what the M sub L was, or if we were told which electron specifically, the plus or minus, we could narrow down the list of valid quantum numbers. But since we only had information pertaining to the N and the L, when it came to the M sub L and the M sub S, we had to keep it as generic as possible. We didn't know specifically how to narrow these pieces down, so we, as per instructed, had to write down all of the valid combinations. Okay, we've been through 2 example problems today. We've talked about how each of these quantum numbers fits together, how they can be used to label the orbitals that electrons can occupy, and again, to kind of bring this full circle. In talking about each of these atomic orbitals, what we really were trying to get at is where can the electrons be in your atom, and, all depending on where the electron is, where can it move to once it absorbs energy, or where can it drop down to once it releases energy. So long as an electron is in a lower energy state, it could jump to, and I'm again saying in real generic terms, your electron could jump up in energy to n equal to 6. It could jump up in energy to L equal to 3. It could sidestep in energy from this -2 to the -1. By introducing more coordinates, we have now introduced more ranges of motion for the electrons as they gain energy and lose energy. And in opening up all of these different energetic pathways, at least in our mathematic descriptions, we are now better able to match the observable behavior of matter. The emission spectra that we've talked about previously, Bohr's model only worked for hydrogen. This new model, with all of our new ranges of motion, works better for all pictures of matter, all different types of matter. We can't still describe matter perfectly. This is why quantum chemistry is still an active field today. We're always trying to refine our equations and refine how we can describe matter using mathematics. But this step in the 1920s, 1930s was a huge step in the right direction, and this is still the foundation that we are working off of today. All right, with that, we have a couple of section review problems. So the quantum numbers versus the atomic orbitals. If you want to be working with the quantum numbers, the N, the L, the M sub L, and the M sub S, these are the first set of example problems. The atomic orbitals is more if you want to work with the pictures. If you want to get to be more familiar with all of the different orbital pictures, this example problem, or this set of example problems, is going to be for you. All right, as always, if you have homework, do your homework. And until next time, class is dismissed.